This is the New Quantum Era, and I'm your host, Sebastian Hassinger. When we talk about scaling trapped ion quantum computers, the conversation almost always lands on the same things. How many ions your trap can hold, how clean your lasers are, what your gate fidelities look like, how aggressively you're chasing error correction. Those are the right questions, but there's a quieter set of questions sitting underneath all of them. Questions about trap design and the tools used to design them, about the software that translates a physicist's intuition about electrode geometry into something a fabrication facility can actually build. Today's guest, Daniel Faircloth, has spent his career on exactly that quieter layer. Daniel is the co-founder and CTO of Nullspace, a company that spun out in 2023 from a defense contractor and that closed a $2.5 million seed round in August of last year. Their flagship product, Nullspace ES, is, as far as I can tell, the only commercial electrostatic solver purpose-built for ion trap design. But Daniel isn't a software person who wandered into quantum. He started in computational electromagnetics, did his PhD at Auburn, and ended up at the Georgia Tech Research Institute, where he was a co-author on a 2013 New Journal of Physics paper demonstrating ion transport through a microfabricated X-junction surface-electrode trap. So he's actually been inside the hardware. He's felt the difficulty of trying to design these things with tools that weren't built for the job. What I wanted to dig into with him is a question I've been pondering for a while now. Is there a version of electronic design automation software, or EDA, very commonly used in semiconductor design and classical computing, that's emerging in the quantum space and is analogous to those simulation and design tools that make modern semiconductors possible? And if so, what does it actually look like when you build one from scratch for the physics of confining single atoms, nanometer ion heights, millivolt precision, shuttling voltages, geometries that legacy solvers were never designed to handle? We had a conversation with Izar Medelsi a while back on quantum elements, which is another entrant in this space, but that, of course, is coming from the superconducting direction. So I wanted to talk to somebody who's focusing on the trapped ion space instead. We get into the technical guts of the latest Nullspace ES release, including a roughly 5 times memory reduction from pairing high-order basis functions with their compression solver. We talk about the awkward commercial reality of selling neutral simulation infrastructure to companies that are direct competitors with each other. And we touch on the bigger question of where this kind of tooling goes next, whether Nullspace becomes something like the ANSYS of quantum hardware, or whether it stays a sharp specialist serving a fast-moving field. A lot of the public quantum conversation lies at the level of the qubit. This one lies at the level of the engineering that has to be right for any of those qubits to actually function correctly. Before we get into today's conversation, this episode is brought to you by OutShift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector, from drug discovery to material innovation to complex financial modeling. Classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. And now here's my conversation with Daniel Faircloth. Daniel, thank you for joining me. It's great to have you on the show. I think you're the first electromagnetics computational researcher that I've had on the show. So I'd really like to get a little bit of backstory for how you sort of found your way into quantum computing from an electrical engineering sort of starting point.
Yeah, sure. Well, thanks for having me. I'm truly humbled to be here. Yeah, I think the story, I was an electrical engineer by training. In grad school, I was working on the combination of computational electromagnetics and novel optimization techniques, basically to do interesting device design. Things that you can go to a textbook, you can see, oh, here's kind of a basic antenna or what have you, and you can kind of see, oh, this is how you would parameterize it if I wanted to do a basic optimization. And we were trying to really sort of break that mold and say, well, if you give powerful electromagnetic simulation tools and powerful optimization tools to an already well-versed and trained electromagnetics engineer, whatever their interest may be, can you effectively turn them into, a super engineer and, unlock creativity as far as what they're able to optimize. And so, in grad school, I was working on these types of problems, and I had kind of have a distinct memory of sitting at my desk and thinking, man, it would be so awesome one day to start a company that basically does this. And of course, at the time, I at least knew that I didn't know anything, and I didn't know enough to embark on that journey. So, if you're in the US and doing graduate work in electromagnetics, you're probably going to go work in the aerospace and defense industry. And
Right.
so that's where I started, and worked at a
That or
great
telecom, right? I mean, you didn't get
right,
swept
yeah.
up in the 5G deployment, I guess.
Right, yeah, yeah. Got moved into the defense industry and um, worked for a great company, and eventually, wanted to tackle um, complex electromagnetic R&D problems. Wanted to see that R&D turn into fielded systems. Actually make it through the valley of death and turn into real world things. And so I um, went to work at Georgia Tech Research Institute, GTRI, and started there in an antenna group, was doing a lot of computational electromagnetics and design work there. Interestingly, that group, that lab that I worked in also had a quantum group that was in the early days of working on ion trap designs. And I got to working with those people and was looking at the way that they were modeling the design of ion traps, and observed all the limitations that they were struggling with. There's the so-called gapless approximation, where you're taking an analytic formula and you just sort of assume the world is an infinite metal sheet, and you kind of trace polygons in that. And of course, that is okay for roughing out an initial design, but it doesn't hold water for too long. And the other tools that were available at the time were just really severely limited. And so I kind of just thought, I can maybe write a little prototype code and see if it helps this group move forward. And next thing you know, that prototype code is snowballing into this whole effort to build a true ion trap design software package that we were using internally. And I've had the opportunity to work with some great folks that helped. I wasn't a computational scientist or a quantum scientist by any stretch. I'm just electrical engineer. So, but I knew how to write modeling software, and so they were teaching me things about what's important. About the ion trap world and the things that they care about.
The shortcomings of the existing methods for simulation or optimization, did that remind you of the sort of what you were finding in your graduate work, sort of like the question you asked about if you gave more powerful, more accurate tools to an electrical engineer, would you turn them into sort of a superhero engineer? Was that sort of the same kind of whatever cutting corners or over approximation that you were finding in the current the existing ion trap tools?
Yeah, to a large extent, that was the case. There were there was essentially no optimization capability that existed. if anybody was doing optimization, it was, pretty local optimizers, pretty basic stuff. And then, on the physics modeling side of things, we had, you know, kind of gross approximations, and then tools that weren't designed for ion trap design by any stretch. And so we're kind of, the community is sort of trying to shoehorn the ion trap design problem into these tools that weren't built for that. And to get to the point where you can design the architecture, the layout, and be able to produce reliable control voltage solutions, so that when you go into the lab and you're dealing with, limited resources in the lab, you have a really great starting point from the simulation. Essentially none of that existed, or it existed in such a severely limited fashion from an accuracy and scale standpoint.
Was that, yeah, I was going to say, was that a matter of the existing tools were more around antenna design for, a telecom or aerospace kind of application, and this was literally trying to hold individual atoms in a field and manipulate? Was it just a matter of the extreme difference of scale?
In a way, I mean, there were some tools that were built for electrostatic simulation, but they weren't. I think, to be fair, and from those tools designers' standpoint, the origin of those tools, they weren't thinking about ion traps and the subtleties that are involved there. How do you predict the ion height to so many nanometers, and how do you create shuttling voltage solutions to so many millivolts of precision? There's just a different class of size scale. Different physics are involved.
And so, did you write some of these simulation optimization tools as part of the paper that you co-authored in 2013 in the New Journal of Physics, sort of demonstrating that it was transport through a microfab X-junction trap, I think, at GTRI, right?
Right. Yeah. Yeah. Those tools eventually led to that work. At that time, one of the big problems was this whole idea of how are we going to turn a corner? An ion is going to have to turn a corner. If you think of an ion trap, this is my electrical engineer gross over approximation, but if you think of an ion trap as a fancy train track system, or city streets, and the ions are being shuttled around, you need to be able to turn left and turn right as you grow and scale. And it was just sort of that simple sounding problem that was very difficult at that time. And how do you get one of the problems was, how do you get the ion to turn but not get heated in that process, and you lose the ion.
Right.
Too much energy is imparted to the ion and it goes flying around the trap, or something like that.
I'm getting
And
an image of like a matchbox car going down a plastic track and flipping
exactly.
over.
That's the exact image in my mind. You're in a race car and you sort of lose control and you go flying off.
Yeah.
And there were some papers leading up to that had these these heating equations in them. And I just kind of naively thought, well, what if we use some of this geometry and topology optimization stuff that I'd worked on before, and map it to the cost function of ion heating? And so the name of the game then becomes, it's kind of a two-stage optimization. One is, can we design the geometry of the trap to put you in a favorable position for being able to then optimize control voltages to turn a corner?
How much of a bank do you need on the track?
Right. And, there were several other engineers and scientists, that were contributing to this problem. And I was just, part of the fun in designing this optimization process. And it was successful. That translated into the lab. And of course, there's always discrepancies between simulation and the real world, and so the guys in the lab, that team worked to take that sort of initial simulated solution. Uh, we got the trap built, and then they had to do some tweaking on all of the control voltage solutions, and then we were able to demonstrate, turning a corner.
That's really cool. And just to frame this, that X track, that was a sort of an early attempt to break the scaling challenge of ion traps, where before it was just a one-dimensional trap, and there were just physical limits. You couldn't really get more than, I think, 30 roughly ions in it in a single 1D trap. So the idea was to sort of cross two single-dimensional traps into this X, and then be able to, as he said, sort of shuttle the ions into one of the side tracks as you move things back and forth, just to increase the overall capacity, I guess, and also just connectivity, right? To sort of increasing the capability of the overall machine.
Right. If you think of, the estimates, even today, where we as a community are still chasing this problem, although obviously in 15, 16 years we've made massive strides. But if you just think of the algorithms that are theorized to provide practical value, in the world, and then that gets mapped to, okay, given heating rates and error control algorithms that have to be implemented, and then you're ultimately mapping that to, well, how many ions do I need in a practical trap to then translate to implementing these real world algorithms, and
It's a lot.
it's a lot. Yeah, just
Yeah.
to put it mildly, it's a lot of ions, and the community's kind of doing battle of like, how many ions do I need given these heating rates and these error correction schemes and all of that, and ultimately, from my perspective, if I sort of view myself as I'm creating a tool that allows the city planner, so to speak, to lay out the city plan for how this is going to look, how this architecture is going to look. Um, Being able to give them a tool that is very accurate, coupled with optimization strategies for being able to design these things, it just makes that job easier. Lets these designers scale up.
So take me from that 2013 paper and the tools and the software that you wrote as a part of that effort to actually the product or productizing that code. You did that in another company, right? And then you spun out Nullspace. Is that right?
That's right. Yeah. So I co-founded a defense contractor called IERUS Technologies, and at IRIS, we were, as that still are, designing next generation RF devices for aerospace and defense industry. And just broadly speaking, in terms of the scale of simulation, the accuracy requirements that exist to be able to design next generation RF systems, you know, all of those problems, when you kind of describe it at that level, all those problems exist in the RF world from a simulation tool perspective as well. So in the early days of Iris, I had departed the quantum computing world for a while, and in the early days of Iris, we started tackling these RF design problems, and we're working on the technology that ultimately would spin out as Nullspace, and it was RF focused. We're working on radar cross section, we're working on antenna design, etc. And then, an old friend from GTRI who had since moved on, Curtis Volan, who's a co-author on that cross junction paper, called me up and said, "Hey, I are you still working on these kind of tools? Like, there needs to be a tool like this." And he kind of really spearheaded the revitalization of that. And we had been developing technology for the RF side of things that would translate very well back onto the quantum side of things. So we took advantage of things we were already developing and created what is now Nullspace ES. And we incubated that uh, through IRIS for several years, and then about 3 years ago, both our EM product and our ES product had reached a level of maturity where we said, we should spin this out as a commercial company and
Yeah.
let
And I
the
suppose the
world have
market
access.
conditions of quantum computing also would be a signal that it was time to spin it out. I mean, the reason I wanted to have you on is that I've been really interested. I just had Izar Medelsey from Quantum Elements on a couple episodes ago. They're doing, sort of, they describe it as digital twins of mostly superconducting qubits. I think there's application in other modalities as well, but it's similar sort of recognition that lab space and resources and time and people are scarce and should be used in very careful ways, and as much simulation can play an enormous role in making the most of of those lab resources, those real world resources. And frankly, as soon as I saw this sort of category emerging, there's a couple other companies that I think are in this general group. It felt like a natural extension of EDA, right? In semiconductor design,
Mhm.
there's all kinds of simulation and design tools that are, absolutely, you can't build a 23 billion transistor chip without these
Mhm.
tools. And it feels like, we're going to go through this evolution of sort of adapting to the specific requirements of quantum computing in the same way. We'll build the same sort of tool chain for the modalities that turn out, that are around today or exist in the future or end up being the ones that hit those commercial values. So was that part of your buddy's sort of pitch to you, is that this is going to be needed as the industry sort of matures and becomes more of a commercially uh, uh, but a productive kind of environment?
Yeah, he was working on solutions to problems to achieve, really the first commercially viable ion trap based quantum computers. And then just over the evolution of 6 or 7 years that have passed by since that all got started, I mean, you see how many companies have spun out, how many quantum research
There
groups
are
there are that
100
are.
hardware vendors now, roughly, give or take.
Yeah, it's been amazing to see how it's evolved and all the different modalities. And so it's interesting, you have the different modalities that are competing, and then within that, there are, in number of companies that are competing given an architectural approach. Um,
Yeah.
so
Yeah, and you
yeah.
mentioned sort of the productization, the maturity of the technology within Iris before the spin out. I was reading up on your 2025 R1 software release, and there's sort of a 5 times memory reduction.
Hmm.
That's really impressive. That's I'm assuming that means the simulation requires 5 times less memory. Is that right? So
Right. Yeah,
yeah.
from my perspective, we have a solver that provides sufficient accuracy for a real industrial grade solution to ion trap design. However, you know, all the hunger of quantum scientists to be able to design larger and larger architectures is unbounded. So, given that constraint, we needed to improve the efficiency of the solver while maintaining or even improving the accuracy. And so we leveraged our existing compression solver, which is really kind of the key to our success here, and then added high order basis functions and got those high order basis functions to work in concert with the compression solver. So you're kind of getting the best of both worlds, and ultimately that led to the memory reduction and a speed improvement. To allow simulation of larger and larger traps, which our customers
Right.
are doing.
Yeah, yeah, and I guess you mentioned sort of the amount of effort and different sort of innovative approaches to getting scale and performance out of ion traps. Is that sort of the main way in which the customer requirements you're trying to fulfill are the ability to simulate larger and larger systems?
Ultimately, yes. The first challenge we had to tackle was the accuracy requirement. They need to be able to rely on the potentials and fields that we're outputting to be able to design their motion control solutions ultimately. And once we had a good handle on that, it became a matter of scaling. And the idea is scale ever and ever larger, or in some cases, be able to produce submodules, so more specialized solvers that maybe handle some early stage design aspects of the problem better. So, if you think of the design challenges, I may ultimately need to design a very large trap. I mean, that's going to be the case. But I got to start with some module level simulation. But those module level simulations themselves are becoming more and more complex. So, how do I enable more sophisticated designs, both at the small scale and the large scale simultaneously? So, these are all challenges
Hmm.
that we're tackling as we move forward.
Yeah, and I mean, it's also it seems to me like it's a complex sort of marketplace from the perspective of you're enabling your infrastructure, right? Your design assistance, your simulation, your customer base are competitors with one another. And
Hmm.
like you had a webinar recently with Oxford Ionics, Curtis Volan, demonstrating Nullspace. How do you sort of manage the sort of the fact that customers are all your customers are potentially competitors with one another, and that sort of shared tooling but disparate kind of commercial gain goals and even architectures.
Right. We face this on the RF side too with our null space EM solvers. So, in some sense, both solvers, face the same challenge of we're we're enabling competitors to compete with each other more effectively. Yeah, and one of the perspectives on that, I would say, is that you know, from a tooling perspective, a rising tide floats all boats. So the better we can make the tool, these companies can do more. Maybe they'll come up with new and innovative solutions that differentiate themselves from one another, and one will achieve some competitive advantage in some area, and the world will benefit from that. And I think that's ultimately what we're trying to enable, is to allow more sophisticated designs to achieve practical value
Right.
and
Well, and I
let
suppose the
everybody have a shot
the
at it.
alternative in those kinds of scenarios is for somebody to roll their own, grab the Python tool SDKs and libraries and whatever else, and build something that's their own internally, and they risk not having best in class because you're focusing solely on this simulation and solvers and optimizers, and therefore you're putting more sole focus on that than trying to build an entire fully integrated command computer. So I mean, I definitely see the risk of not using your tools if your competitors are right. I'm really curious. Like you're in a position where you're coming out of a defense contractor, and the tools that you're building are still potentially seen as dual use. Is that advantageous, or is that complex, or is it both? Are there advantages and disadvantages to that kind of dual use categorization as a technology vendor?
There's there's definitely pros and cons. We want to enable um, our customers to have the best technology possible, and these different markets at different times in their evolution offer different levels of challenge. It used to be I think the old thinking was that the in the U.S. at least the defense class of problem or the space problem, NASA and thinking all the way back to space race, that the government was leading the charge on all of the best technology development. And I think there are certainly still places where that applies, but we also see where the commercial world is leading, and essentially the defense market contributes to the commercial world and vice versa. And as a tool developer, having our feet in as many different markets as possible, I think ultimately serves to our advantage in being able to learn lessons in different places to push forward the technology for better, faster, more accurate simulation.
Right. Right. Yeah. And so you've come out of the ion trapping world, and the product is still sort of bread and butter is ion traps. But I mean, I know, for example, there's an open source electromagnetic simulation that the Amazon Web Services, the Center for Quantum Computing group under Oscar Painter, put out called, I think, Palace.
Hmm.
That's for electromagnetic simulations as pertains to superconducting qubits. So, do you see other modalities as sort of adjacent market opportunities for sort of product development in the future?
Definitely. And we also, I mean, just back to your point about why doesn't a quantum computing company in-house the development of their own solver? And we have a similar problem of, we've got the same or a similar set of opportunity costs in front of us, and we have to weigh where we spend our time investment. And the ion trap architecture design problem that Nullspace ES solves is certainly not the only tool in the tool chain, even just for ion trap architectures. So there's a roadmap question in front of us about how much end-to-end design capability do we invest in and offer, even just for ion traps. Never mind, do we invest in architectural simulation design tools or quantum EDA type tools for other architectures, and then just extend that across the entire electromagnetic spectrum, and it becomes a feast of opportunities.
Yeah, and a puzzle to be solved in terms of where to put your focus next as
And
a small company. That is always
indeed,
a challenge. And I guess so. Last question, then, along those lines, if you sort of think out 10 years, like is are you sort of more imagining null space as being like the NSYS of this space, like an end to end, a stop shop of all of the tools that you need for building the tool chain for your particular technology, your own in-house R&D, or are you more of like a deep specialist in one particular area that's maybe part of either a federate or even an acquisition by somebody that's putting together that whole suite?
I think one thing that we've seen in the industry over the past several decades, but in particular the past 5 years, is the acquisition approach of the large EDA simulation providers. They provide good solutions, but oftentimes these solutions are sort of bolted together in awkward ways. Users complain about how the end-to-end workflows work or don't work. And there's an opportunity there for us to address those uh, pain points that our users are experiencing across a lot of different disciplines, quantum computing and RF being the two that we're focusing on. Long term, there's definitely a need in both of those marketplaces for more tightly integrated multiphysics simulation as we see an evolution of the densification, if you want to call it that, of these devices, how they interact with each other, how your iPhone gets hot and you're wondering what is that doing to to my iPhone. As an antenna designer, I know it's having an effect, and being able to understand these questions, and of course, heating in the ion trap world is the great nemesis. So how are we modeling the electrostatic fields, the RF fields, the Joule heating that's going on in the trap, and being able to provide all of that in an appropriate fidelity one-stop shop for the designers. We don't want them to have to go to a bunch of different tools and try to kind of piece together dealing with file format exchange issues. And in this physics modality, I modeled these geometric features. And this one, I have to clean up the CAD model in some way. And then you always wonder, did I really model the same thing? We're trying to put all those issues to bed over the long haul.
That's crazy. I mean, I think about sort of like creative pipelines, like in, Adobe products, for example, which can be painful. And that's just pushing bits around on a screen. Like it's just, does the font look right or not? I can't imagine how complex it is when you're talking about modeling an actual, system from nature or physics or whatever. That's really amazing. It's quite a challenge. I think, it's really interesting what you're doing. And, as I said, the quantum EDA space, I think is overlooked at the moment. So I'm trying to do these kinds of interviews to bring some more attention to it because I think it's incredibly vital. So thank you so much, Daniel. This has really been very interesting. I really appreciate it.
Yeah, thanks for having me, and thanks for your efforts to educate the world about these challenges.
Thanks again to Daniel Faircloth for the time and his candor. This episode was brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector, from drug discovery to material innovation to complex financial modeling. Classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. The line from the conversation that stuck out for me was Daniel's framing of the ion trap as a fancy train track system. Ions turning corners, voltages tuned to keep them from flying out, because it captures something that easily gets lost in the qubit count race. Every one of those trajectories is the output of a design tool, and somebody has to build that tool. Daniel and the team at Nullspace are doing that work, and it was a pleasure to make the layer underneath the hardware a little bit more visible. You'll find full show notes for this episode at newquantumera.com, including links to the 2013 X-junction paper, the Nullspace ES 2025 R1 technical brief, and the recent webinar with Oxford Ionics' Curtis Volan, where you can actually see the solver in action on a surface-electrode trap. If you want more conversations like this one on quantum engineering, simulation infrastructure, and the unglamorous layers that make scaling possible, sign up for the newsletter at newquantumera.com to get new episodes and occasional essays in your inbox. If you got something out of this episode, please subscribe wherever you listen, leave a rating, and share it with someone in your network who cares about the engineering side of quantum, not just the headline benchmarks. It genuinely helps the show reach the people it's meant for. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.